Okay, so today we're going to be looking at our substitution and elimination reactions. And while we are doing it for alkyl halides, we will see that this type of reactions, these substitution and elimination reactions, happen anytime we have something that is a nucleophile on there. It's just that the easy ones to do are with alkyl halides. All right, so we are going to be talking about things that leave easily, but we are mostly just going to be focusing on that row right there. Okay, now the reason this is actually a similar reaction is because that electronegative or bulky species creates a very electron withdrawing group, makes that bond weak, and more importantly, weak enough that when it does break, those electrons go with our halogen and leave somewhat a carbocation behind, or carbocation-like, or electrophilic location. Now, when we talk about our main reactions in this chapter, substitution and elimination, we are talking about these two things. Our halogen is going to be replaced with something that's nucleophilic in a substitution reaction, or a nucleophile causes an elimination of an adjacent hydrogen, forming a double bond. And that's the two classes we're going to look at. Now, we're going to start with substitution at first. Now, our focus on substitution is going to be just on these guys right here, our alkyl halides, and more importantly, these two. And we'll see why those two are a little bit more prominently featured here in just a second. All right, so our first type of reaction we're going to look at, first type of substitution, is called SN2. Now, the SN2 is very specific in what it means. It does actually mean nucleophilic, so it is nucleophilic substitution. That's what that N is for. And the 2 comes from the fact that the first substitution reactions we're going to look at have an experimentally determined rate law that involves both our alkyl halides and the nucleophile. And that rate law does tell us that the concentration of those two are important, and it also tells us that the slow step has both those involved in it. All right, now our experimental data helps us a lot of things, so much so does some of the discoveries we find when we study it, because we're going to see that this can help us explain exactly what's going on in the actual reaction. Now, the first thing we're looking at right up here, we find out that methyl halides are much more reactive than primaries. Both these are primaries, and much more reactive than secondaries or tertiaries. Matter of fact, tertiaries are so non-reactive, it's kind of safe to say that doesn't even happen. That will not do a substitution reaction via the same SN2 system. Something else we discover, if we start with a stereoisomer of a alkyl halide, we will find that we get an inversion of that reaction center. Now, right now, it is going to be a full reversal of the letters because, for the most part, our halogen will be the high priority, and we're going to be replacing it with another high priority. But it's not right to say it causes an inversion of the determination. It's an inversion of the stereocenter. It actually might end up in some really rare cases with the exact same letter, even though it's an inversion of the stereocenter. Okay, so to understand what our discoveries tell us about how this collision happens, we're going to look at a few things. So let's remind ourselves of our terminology. We are talking about the nucleophile, OH in this case, attacking the electrophilic carbon, causing the bromine to leave with the electrons. So that negative species kind of gets substituted with this negative species, or the alkyl halide gets substituted with an alcohol. Now, we would expect that simply because the negative reaction. But what we're saying is our rate law says this happens in our slowest step. That must be the case because both those are involved in our slow step. So we're going to take it a step further and actually say that the backside of the sp orbital that the carbon was bonding to the halogen is what the nucleophile attacks. So remember when we drew our hybrid orbitals way back in Chem 1 and 2? Well, we're saying the halogen was attached to the big side, and then our nucleophile, in this case the OH, actually attacked that small little lobe that's in the back. Now, reason this is important to say this is this actually because is to see how that backside attack happens and how the inversion happens. Because remember how we said the stereocenter is inverted? We're thinking about the hydrogens here being almost like an umbrella being caught in the wind. Normal downward thing. And then when the wind blows it and it flips upside down on itself, that's kind of what happens in our mechanism. And that explains why there's a stereocenter reversal. Now, that bimolecular transition state was alluded to in the rate law. Anytime you have a rate law that actually has two components, that implies that both those components are found in the slow step, which is what we found in this case. The slow step actually involves the hydroxide ion, the nucleophile, and the alkyl halide. That implies that there is a transition state where the carbon is bound to both those. All right, that would also help us understand this backside attack and whatnot, why bulky substituents in primaries, secondaries, and tertiaries react the way they do. And it's simply because if we need to come up with this little tiny little orbital that's here, it's very beneficial if there's nothing in our way. And if you think about the tertiary one, you got those three methyls, and it's just not going to get in there, or three carbon groups. Just this, we're not really going to be able to make a backside attack. So we need that less hindered carbon to actually get our nucleophile in there. All right, so back in 1937, Hughes and Ignal proposed a mechanism for SN2. And it's got our two main things going on in here. So the rate of substitution reaction depends on the concentration of the alkyl halide and the concentration of the nucleophile. That indicates they're both involved in the slow step, or the rate determining step. And as the alkyl group becomes larger, or as the hydrogens of the bromomethane are successfully replaced by methyls, so that's from primary up to like tertiary, the rate of the substitution goes down, and the rate of the substitution with the nucleophile goes down. Okay, so we're going to predict this based on just this general idea. A methyl halide is going to be most reactive, primary and secondary a little bit more, and tertiary are too unreactive to do that. So if we see a tertiary, we just basically say it cannot do SN2. Methyls and primaries do it very easily. Secondaries, we have to typically encourage it. Now, bottom one, these are both primaries because the halogen is only connected to a carbon that's connected to one other carbon. But since this is just one carbon coming off there compared to an ethyl group, we're going to actually see that it's a little bit easier to react with. So fewer carbons off of that position, the better. All right, now, reason that happens has nothing to do with the stability of the products. We would actually predict any alcohol to be more stable to an alkyl halide, and that's going to be the case no matter what our group is. What slows down these reactions is the increasing activation energy we have to put into the molecule when our transition state is less stable. So when we have more R groups, the hydroxide, it's harder to get it in there, the harder to get the nucleophile in. Okay, inversion of the stereocenter is very predictable based on this. Now, do keep in mind, you would want to recalculate the rotation in many cases. The reason this one's replaced a full switch of the letter is because, well, that's my high priority. Hydrogen's my 4, this would be 2, and this is 3. You will notice that 4, 3, and 2 are identical. This is still high priority. That's going to happen almost all of these because it's almost guaranteed that right now halogen will be our high priority. And then the nucleophile, which is mostly going to be hydroxide right now, is also going to be high priority. But that's not the definite case for all SN2s. That's why it just says inversion of the stereocenter. All right. So our main factors that affect whether or not it's going to speed up is what we're going to define as the leaving group. That really is the halogen. Certain halogens react better than others. Certain nucleophiles react better. There are better nucleophiles. We are going to see that the solvent does play a factor into it, and steric effects are going to factor in there. So we're going to expand our SN2 understanding. We got a general idea of how the reaction occurs and what the mechanism looks like, and even what the transition state looks like. We're going to see how that relates to all of these. All right, first thing, the leaving group. Even though this is talking about the halogen, the reason we refer to it as a leaving group, it is what comes off. What we need to see, what we see factors in here, the stability of this ion to exist greatly affects the rate of the reaction. And it turns out a fluorine negative is a little bit less stable than an iodine negative. And it really is just the sheer size of it. Iodine is so much bigger, it's easier to float around in the solvent all by itself, and it's quite stable compared to fluorine. And just because of that, we see that the alkyl iodides are much more reactive than the alkyl fluoride. It is actually to the point where we almost avoid this because it can react so fast it might eventually be dangerous. And we avoid using this one because most of the time it won't do anything at all without special reactions. But it is related to that leaving group. Now, both cases we will find times where they're used. We're just going to be a little bit more careful, both those, how we get the reaction going. All right. Our nucleophiles, all the ones we're looked at so far in this chapter have just been OH. But any nucleophile that is strong enough will actually do this. Now, we will actually see that SN2 needs what we consider strong nucleophiles. Now, a strong nucleophile is one that definitely has those negative charges on those, but any one of these that has those negatives would actually be somewhat strong. Now, these guys really aren't. We're not going to see those behave as strong nucleophiles. Even NH3 might behave like a strong nucleophile if we get it concentrated enough. But all these others, they're kind of weak nucleophiles. Even this one's somewhat weak of a nucleophile, even though it's negatively charged. All right, so strong bases are typically the strongest nucleophiles, and that's the general rule. A strong base is our best nucleophile. So when I ask for a strong nucleophile, you're looking at the strong bases as well. Now, anything that has a lone pair on it that's available is at least a nucleophile. Weak nucleophiles are actually just more like weak bases. All right, now here's something interesting. When we want to replace a nucleophile, a halogen, we could actually replace them with other halogens. All right, so now if this is a fluorine and this is an iodine, we see something interesting going on, because to actually get that fluorine to come off, and we know the reactivity is low, we'd have to get this big, huge, bulky thing in there. Well, fortunately, iodine is big, so there will be a significant overlap long before that fluorine gets kicked off. So that transition state has a little conflicting factor. The iodine's big and bulkiness is going to allow that transition state to actually exist in a very elongated state while the fluorine's still attached. And on the other extreme, even though fluorine is tiny, 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 iodine is already pretty far away. So we're almost to our transition state, and we don't need to get a huge amount of overlap. Nonetheless, fluorine's a little bit hard to get in there because it is just so darn small. We don't really get much of that overlap occurring. So we will find when it comes to nucleophiles, even though iodines react the fastest, we'll also find out that iodine is a better nucleophile just because it's a little bit bigger. All right, so we got a couple things going on here. So, and this is viewing these as nucleophiles. As the size goes up, they actually decrease their basicity, but that actually does the exact opposite thing with regard to our nucleophilic properties based on whether or not our solvent is capable of hydrogen bonding or not. Yeah. Isn't that interesting? We actually can affect the rate of a reaction by choosing a solvent that's aprotic or protic, one that's capable of making hydrogen bonds or one that's not. Now, the reason that factors into it, we think about our halogens and something that can do hydrogen bonds, like an alcohol. Alcohols with those strong dipole-dipole interactions, those hydrogen bonding interactions, they will surround something very electronegative, like a fluorine, with very strong intermolecular forces. If that's the case, now the fluorine is actually too busy bounded with these strong interactions to actually react with our substance. Yet, if I go to iodine, I have a complete opposite thing, because even though iodine is still a negative ion, it will make a weaker ion dipole interaction with hydrogen bonds. Therefore, the iodine would be actually more available. Now, we can reverse both of these by just choosing a different solvent. Had I, instead of using alcohol, used something like an ether, we would see the ether here makes a stronger interaction with the iodine and a weaker one with the fluorine. All right. Other things to factor into it. Even though the tert butoxide ion on the right is a stronger base than ethoxide, it's actually a weaker nucleophile. And it's a weaker nucleophile for our substitution. And that's really a lot more to do with the size of it. So remember how we needed to do that backside attack? Well, if I have this big, huge thing coming in here to try to do the backside of attack of an alkyl halide, let's even think about a tertiary one. This thing is so big, it's going to be having a difficult time getting in there. So even though it's a strong base, its steric properties forbid it from doing a backside attack very easily. All right. Now, our reactions with our strong nucleophiles are varied. Any one of our halogens, with the exception of fluorine, we typically don't try to do these with fluorine, but chlorines and iodines and bromines are all used. We will find almost any one of our strong nucleophiles can do an SN2 type reaction. All right. Next substitution reaction is what we're going to refer to as SN1. Now, the N does actually mean nucleophilic, but we are going to see that these are mostly poor nucleophiles. Something like water would definitely not even do SN2. Water is a weak nucleophile, yet SN1 likes weak nucleophiles. All right, we are also going to find out that our alkyl halide is typically hindered. So it's like tertiary, secondaries or more. And we will still see the same type of thing as substitution reaction occurs. Now, both these things, being that this is tertiary and a weak nucleophile, would be two things that we would say would not happen under SN2. So if this was going by an SN2 type reaction, we would expect it to be ridiculously slow just because both of these are negatives. Yet this is actually kind of fast by comparison, or faster than what we would expect. So something else is happening. All right, now the first thing we're going to see is that the 1 on that SM1 comes from the fact that the rate law is totally different. The rate law only involves the concentration of the alkyl halide, and the nucleophile has no effect whatsoever on the rate. Now, chemical kinetics implies that the slow step of the reaction only involves the alkyl halide. So that does actually mean we have a slow step that only involves that, and it makes something else. Now, whatever it makes must later do something with the OH. So that must continue on down here and must later on do something with the, I said OH, but nucleophile. But it doesn't happen in the slow step, because if it happened in the slow step, the nucleophile's concentration would be important. So that second step must be a faster step. All right. We know from that previous slide that the tertiary alkyl halides undergo it more rapidly. And we also know another piece of our experimental evidence is that if we create an enantiomer, we get a racemic mixture or close to it. I'm going to put close to it. So that does imply, so let's say we start with an Rx that was definitely S. When we're all done with our water, we would get ROH, R, and S. We get both. All right, so that tells us that we're not expecting or don't see a backside attack, at least not the same way as SN2s. All right, let's propose something and see if this makes sense about what's going on. All right, the slow step, we know it involves just the alkyl halide, so that's what we're showing. The alkyl halide must involve the bromine just ripping off all by itself, making a Br minus, leaving a carbocation behind. And that's believable because we said that this likes to be tertiary, and we know that tertiary carbocations are actually stable. So that is a believable thing. And that's also exactly why we would not see primary or secondary do this, because primary and secondaries don't make stable carbocations. All right, then our step 2 comes in. The nucleophile adds to it. Now, in this case, when this nucleophile adds to it, it is going to go on intact. So it is going to look like a water molecule. And that creates an O that actually has 3 things on it. So there is still a positive charge. We'd have to have a second water molecule come in and deprotonate that. All right. Now that we have this proposed mechanism, let's see if it makes sense with everything we're seeing. All right, so our slow step is just the ejection of a halogen creating a carbocation. Well, we know that's going to be a difficult prospect because this was a stable molecule. These are not stable by themselves. So that makes sense. It would take some energy to rip it off. All right, but if I actually take a carbocation and turn it into a cation where the charge is on the oxygen, I would predict that to be a little bit more stable. So that should be an easy step. And the next step, where we're just deprotonating the hydrogen or the alcohol, that should be an easy step to predict as well. So this reaction coordinate diagram does seem to follow and flow with what we'd expect our slow step being the creation of the carbocation. All right, so now that we have a mechanism, let's look at the factors that affect the rate of an SM1. Turns out the alkyl halide structure is going to factor in as well. We're going to see that tertiaries are better this time. The intermediate structure is the reason. Tertiaries again. Leaving group still an important thing, and the nucleophile is. All right, so our alkyl structure, creating that carbocation, is an important little complex thing. Since we know our first step creates a carbocation, I'm going to draw it like that, we know that rearrangements might occur. And that's what they're showing here. Because my very first step was carbocation. And what's happened here is we've done a rearrangement. What's essentially happened is, I'm going to change my ink because we moved this double bond, or that bond, to there at the same time as essentially moving this here. So I'm going to draw that, all those carbons in the exact same location. But what's happened is we've now created a bond here, and this thing, even though I have it drawn here, is now bonded to this other location. There's not a, that is a curve. It's supposed to be a straight line. But we ended up with a 1, 2, 3, 4, 5-membered ring with a carbon on 2 different locations. And this could still be considered a cation. And what's happened is our nucleophile came in and attacked that carbocation. All right, but on these SM1s, I just want you to remember, creates a carbocation, it might rearrange. We typically like to try to do an SN1 type reaction where rearrangements are at a minimum. And how are we going to do that? Well, as long as we know there's a carbocation, we're actually going to be able to focus on the fact that tertiaries are more stable and anything that's near it is important on that rearrangements. All right, now, once it's created, go back to my dark ink, the carbocation that is, our nucleophile can attack from either side. And we're either going to get an inversion of that stereocenter or it's going to be maintained. Now, the reason we expect, or we might expect, a racemic mixture is because once we've created this carbocation, you have a 50-50 chance of this occurring. And that is true for the most part. Unfortunately, the second step is actually relatively fast. And the moment that this carbocation came into existence, this bromine's still right there. And what that actually means is that this OH, or the nucleophile, can't get there as easily as it could over here. And simply because of that, we typically see on all SN1s that inversion is slightly more. And it's simply because the halogen or the nucleophile is in the way for a short amount of time on that actual straight inversion or the straight retention. Okay, now leaving group, we're going to see exact same factor as before. That big bulky iodine comes off a little bit easier because it's already pretty far away. And so because of that, alkyl iodides are more reactive than alkyl fluoride. We are also going to see solvent effects are mostly ignored here because our solvent is going to be a nucleophile. So because of that, we choose to use the solvent that is the nucleophile we want to react with. So if I want to put an OCH3 onto this, I use OCH3H. I use an alcohol based on that. But technically speaking, on all SN1s, your solvent is always the nucleophile. We're going to introduce this word, solvolysis. Which basically means solvent is the nucleophile. All right. Now, benzylic and allylic were very special carbocations we had before. We're going to see they factor into this as well because they do make very stable carbocations. They will go through SN2 reactions, no problem whatsoever. And that's mainly because, in this case, that's a primary location and this is a primary location. But if I use that strong nucleophile, we're just going to get straight SN2. It's going to go exactly where we'd expect it to do. We're not even going to do anything at all about the pi bond. We can basically ignore that it exists. All right, SM1 kind of can do the same thing. We do know that ripping this off creates a carbocation and it is stable. We have to watch out for our allylic things. And remember how we said that carbocations can rearrange? Well, that's going to factor into it. Now, I don't have to worry about the benzylic reaction. Where do I have it? I don't have it here. I don't have to worry about benzylic carbocations rearranging too much because what we introduced to last chapter, I'm going to leave that CH2, but I'll move my double bond around. And we could do this 3 different ways. And the last one looks kind of like the top, or that very first one, but just kind of backwards. But all 4 of these carbocations create the stability, but this is the only one the nucleophile will attach to. Don't have to worry about the nucleophile attaching here. And that's mainly because these 3, we've lost their aromatic properties. So neither one of them are going to get attacked by that nucleophile. Only this one does. So via SN1 and SN2, we get the exact same product when the benzylic position. Now on our allylic, we have to be careful. The reason I don't have to worry about it on this particular example is because I got a very symmetrical molecule and both carbocations look the same. But if I were to go with something a little bit different, I get two different carbocations, and they are different. And because of this, both of them get attacked by that OH. So you do get those rearrangements, and you will get two different products in this case. And in this particular one, we kind of would be expecting this mostly to be our major product because of the fewer H's off the double bond. But at this point, there's a little bit more going on just whether just the double bond factors in. So right now, we're just going to focus on the fact that you get mixtures when you use allylic. All right, don't have to worry about vinylic or aryl. That's where the halogen is directly connected to a carbon that has a pi bond on it. There's too much steric hindrance or too much electronegativity from the cloud to allow the nucleophile to come in there. So those two will not do nucleophilic substitution. All right. All right. So our summary of our SN1 and SN2. The 2 and the 1 tells you how many things are involved in the slow step. It also tells us, generally speaking, what the mechanism looks like. The SN2 is always a one-step mechanism. The SN1 is a two-step with possibly three steps because first step, you create the carbocation. Second step, you might create a nucleophile attached that's still a cation. And then you finally get where just the nucleophile is attached. Might be a third step just to do that. The alkyl halide is very different on these two. These guys both like primary and secondary and methyls. This only really likes tertiary or our pi systems, so allylic or benzylic. But on these, we might get rearrangements. And before I put that little symbol to tell you to look at what that transition state is so you can focus on the carbocation, and that you should do the same thing on these. Okay, let's practice some. All right, first of all, I got something like ammonia there, and I'm asking at first, what type of mechanism do we have, SN1 or SN2? Now, we know it's one of those two, and we got a couple factors helping us out. First, that's secondary. And we do have a base. Because this, and it's high concentration, because it's high concentration and it's a pretty reasonably strong base, we know this is going to be SN2. So since this is SN2, I can do something neat like this. I can draw the carbon backbone exactly like it is. I'm going to reverse the hydrogen and the nucleophile that goes on. In this case, it's going to go on as NH3, and then we'll just get that deprotonated and end up as NH2. All right. How about this one, though? My alkyl halide is tertiary, and this is an alcohol, so that's a weak nucleophile. Simply because of that, we know this one's going to be SN1. So I'm not going to go straight to an answer here. I'm going to focus on what this turns into. I'm going to leave everything the same except that becomes a carbocation. All right, now, when we do something like this, we got to look. Is there going to be any chance that this thing rearranges? No, this is a tertiary carbocation, not allylic at all. So I know this alcohol is going to end up attached there. But since this becomes a carbocation, I can see that the CH3OH ends up on both sides. So I am going to see this stays the same. And I can have one of these where the CH3 is exactly where it was. This turns into an OCH3 once we lose that hydrogen. Or this is still up. Oops, that's not a 2 there. 2 is there. CH3 is here, and this becomes an OCH3. Now, technically, I could have drawn either one of these and just wrote the word enantiomer after it, but that only really applies to that stereocenter, right? So this case is a little bit easier to draw both of them out. All right, another one. High concentration of OCH3, and I have a secondary. Yeah, that's a strong nucleophile, so this is going to be SN2. Now, the nice thing about SN2, our nucleophile goes right where the halogen was, just does an inversion. Same reaction, but OCH3, or it's instead of OCH3, it's now CH3OH. So it's still secondary, but because that's a weak nucleophile, this would be SN1. So I'm going to create a carbocation. Now this is allylic, goes back and forth, but we wouldn't actually even see that because of how this nature of it is. But when this is all done, I'm going to see this OCH3, and it's going to be up or down at that position. Okay. When we were talking about our solvent effects, what we are going to focus on mostly is whether or not the solvent can make hydrogen bonds or not. The fact that a hydrogen bond drastically affects how strong the ion-dipole interactions are. Matter of fact, that's really our key feature. The ion-dipole interactions, the stronger they are, the bigger the effect is. All right, so we kind of need the ability to measure how polar a bond is because polarity is related to that hydrogen bond nature. Well, it turns out there is a way to measure it. It's called a dielectrical constant. And the dielectrical constant is a physical measurement. There's instruments that will actually measure what the dielectrical constant is, and it's directly related to the dipole moment most of the time. So we actually can measure the dielectrical constant of various different solvents, and these are just an example of solvents that we might use. Now, ironically, not all these really get used because we either want protic, ones that can form hydrogen bonds, or aprotic. Aprotic just means a polar molecule that cannot actually hydrogen bond. And all the way down at the bottom, I do have hexane, which isn't very polar at all. It does have a dielectric constant of 1.9, and that's really because it's big enough that all those carbons actually, those sigma bonds rotate around and create momentary dipoles. But these are all somewhat polar molecules on here, and the dielectrical constant is related to how strongly polar they actually are. Now, biggest reason these all get used as solvents is because while we do want just two categories, we have some that are cheaper than others, some that are safer to mess with, some that smell better, but mostly their boiling points help us out some because you need a solvent that can handle the heat if you need to heat up a reaction. All right, so the rate of our reaction will be affected by the solvents. Now, this is mainly for SN2, but we will see that all solvents affect the same thing on that slow step. So it turns out if the reactant in your rate determining step is charged, if you increase the polarity, you'll decrease the rate. Now, what I meant by that, let's think about just a sample SN1 reaction. We know that when we start with our alkyl halide, when we finally make it here, we're going to have a charged product. but we're focusing on the transition state. Excuse me. What we find is if we have a much more polar, something like water compared to ethanol, we actually get a faster rate for that type of reaction. And it's really the case of all SN1 type reactions. A more polar substance increases the rate. Now, SN2, not nearly as big of a factor, but we still get the same type of thing because we have a, it's still a charged transition state because our nucleophile is going to go on there. This thing actually has a charge to it. So our more polar solvent does actually affect it. All right, on to our next category reactions, which is our elimination reactions. Now, elimination reactions, what's going to happen instead of replacing the halogen, we're going to have a nucleophile remove an adjacent hydrogen and create a new double bond. And that arrow I just drew is one of the two ways it could happen. All right. Our easiest ones to see is going to be comparable on the 2 of SN2, and we're going to call it E2, elimination bimolecular. Now, the rate law is what gave us the 2, and the rate law is the alkyl halide and the base. That's exactly the same as SN2. It's very similar, except that we will find that this particular alkyl halide is typically tertiary. On SN2, it was primary or methyl. So we know this isn't likely going to be to do a substitution because it can't get to the backside. What happens on E2 instead is the OH attacks a neighboring position. The electrons that had formed that bond form this double bond, and then this gets kicked off. Mechanism looks something like this. It's a nice little concerted reaction that all happens at once, but our nucleophile just rips off an adjacent hydrogen. All right. Now, it will always be what we consider the alpha carbon. Now, what we mean by that, if you treat the alkyl halide as the alpha carbon, the nucleophile, or that strong base, rips off a hydrogen off one of our beta positions. Now, I did say one of, and that's mainly because if I were to start with something slightly different, on that particular molecule, I technically have 2 different alpha positions, or 2 different beta positions. That will actually end up creating 2 different alkenes. We could rip that one off, put the double bond here, or I'm going to rip off the outer one. So we're going to see that the more beta carbons you have, the more possible answers you have. Now, reactivity is still the same for the exact same reason. Our leaving group needs to be stable, so halogens that are bigger and bulkier are going to react faster. All right, now that regioselective, what I mean by that, that's just what we were talking about in that previous slide. I have 2 different beta positions. I have to look at all the possible alkenes that could form. Now, if I keep it nice and simple, like an isopropyl group, I get propene no matter what. We get just that one. But if I do that 2-bromobutane, I am going to get 2-butene, and I'm going to get 1-butene. Now, we will find that stability of the alkenes actually does factor in here. The fewer hydrogens is preferred, so that almost always leads to our major product. All right, now, biggest reason it leads to our major product is because we need to make a stable alkene. Now, all alkenes are relatively astable, but it turns out the stability of our transition state factors into it. What I mean by that, when we actually rip off our neighboring hydrogen, we need to have a transition state that's relatively stable. And what's going to happen is this transition state, creating this little pull on this carbon, having another carbon near it will help stabilize the charges going through that carbon. If it's out by itself, it's less stable. It's harder to actually get that a happy molecule. So it's much better if our carbon that's giving up the hydrogen has other carbons near it to stabilize it. All right, so nice little rule that we're going to introduce called Zaitseve's. And basically it's going to say that our alkene that we make is always going to be the more substituted alkene. So when we have choices of more than one beta position, you're essentially going to go to the beta position that has fewer hydrogens on it. It's got to have at least one hydrogen, but you're going to go with one that has going to end up giving you the best alkene. And if there's ties, you get mixtures, but you pretty much always get mixtures even of the ones that break Zaitseve's rule. Okay, so let's do an example of this because I have a strong nucleophile, but I have a tertiary one. So all of my beta positions come into question. Now, the nice thing is these two are essentially the same because they're both CH3s. So I know that going outside, I'd end up with something like that. But I also know Zaitsev told me that side with with fewer hydrogens is where we're likely going to get the elimination. So I'm going to leave this alone and leave that alone, but make that go down by one hydrogen and major. Now, the only thing I need to do in addition to that is to see, do I have E and Z as a possibility, cis and trans? I don't here because that's a CH2, and I don't here because those are both methyls. So I only get two products where this one is the major product. All right, let's do another one. All right, let's just go straight to our major product. I have the two beta positions. The one on the left has fewer hydrogens, so I have it go there. I'm just going to put major. This one can have E and Z, and we would expect both. But I'd also get, in this problem, I did not write it and say, give me the major product, so we'd have to actually consider that it makes that one as well. That's a 2 on the end. But no cis and trans there, so only one product on the second minor product. All right. Now, this is something interesting. Zaitsev tells us that there's always a direction based on the number of hydrogens. So since this is a bulky one and this is secondary, I would typically think we're going to go over here because that has just one hydrogen compared to 2. And then I would end up with that should now be an H, 2CH3 and CH3. And that seems to follow Zaitsev's rule. But my minor product in this case has something neat going on. So I'm going to rip off that hydrogen, make the double bond go over here. And what's neat about this one is I've created an allylic system. And simply because it's allylic, it is more stable. We're making the more stable double bond, which might have been a better rule for Zaitsev to say, make a more stable pi system. That being an isolated system is less stable, so this becomes the major. So how about on this one? I know it wants to go over here to that beta or there, and I'd normally like this beta, but if I go over here, I end up with a conjugated system to that benzene ring. Double bond. And then all this can be just the same. But that conjugated system is going to be definitely more stable than an isolated system, so that is your major product. All right, Turns out bulky bases also make an exception. Really because that big, huge bulkiness of that tert oxide really can't get in and attack that side because it's less acceptable. So when we use a bulky base, we actually get the anti-Zaitsev product in a far more measurable amount. And it happens no matter what our halogen is. We end up getting the bulky group, on there. I'm looking at these numbers. This should be your major. I have no idea where I got with those numbers. All right, so we can actually call it a bit. The more bulky it gets, the more likely you're going to get to that less stable alkene where the double bond is further out or more hydrogens on it. We also find that alkyl fluorides favor the less substituted side as well. Now, this has nothing to do with bulk, has to do with how that fluorine stabilizes it. All right, because fluorines are so darn electronegative, they actually never really hold that negative charge. That negative charge stays on a carbon, and we will find that carbanions like to have fewer things off of them. Carbanions have an exact opposite stabilization as the carbocations. Least stable has more and more carbons because those carbons kind of force that charge to be out there. If it's like this, it can spread it out to more of those hydrogens. So having more hydrogens on a carbanion is better. All right, so nice little summary. Our alkyl halides and a strong nucleophile, if this is secondary or tertiary, we end up giving an elimination product. Now, for the most part, Zaitsev says most stable double bond. Or how about not double bond? Most stable pi system. Because that'll help us remember that our allylic positions and benzylic positions will factor into this. Now, our leaving group factors into how well this works. So iodine typically really likes to make our more stable product. Bromine chlorine does as well. And fluorine almost likes to make the least stable product. Okay, let's see if we can predict our major elimination product if we use our strong nucleophile with any of these. All right, first one, double bond starts there. And I'm just going to have the double bond go to one of those alpha beta positions. Got to be there. This one here, that would be your beta position. And here, I have beta, beta, and beta. So I would end up with the ring has fewer hydrogens. I predict that to be major. But I'd also get where that goes out. Yeah, those two are the same product. Okay, next reaction, another elimination, is actually E1. Now, if we look at what we're reacting here, this has got a weak nucleophile in it. We also have a tertiary, and we have a rate law very similar to SN1. Problem right off the bat, you might have remembered. This and this are the exact same reactants we use to get SN1. And you would have been right to say that because it turns out E1 reactions compete with SN1 reactions. Now, our mechanism, first step, is exactly the same as SN1. Very first thing that happens is the halogen gets kicked off and we create a carbocation. It's just on E1, instead of having the nucleophile attack the carbocation, it attacks an adjacent hydrogen, rips that off, and creates the double bond. Okay, now the mechanism is going to be driven by the stability of that transition state, and that creation of that pi bond allows this to happen. So that pi bond creates a great little place for that to react. All right. Now, we typically do see that Zeitz use the product as our final product. So that is the same driving factor as we saw as E2. And that's not really going to be too much of an exception. And the nucleophile doesn't really truly affect a lot on this because most of our weak nucleophiles are relatively small. But bulkiness will still factor into it. So if I actually replace water with tert-butoxy, the bulkiness will factor into how it gets in there. All right. Now, transition state is that same first step as our SN1. It's that second step that varies. And because a more stable carbocation or more stable alkene is lower in energy, we do predict it to be the major product. Okay, so we're going to actually see something that the alkyl halide has a preference. It does like tertiaries. E2 also likes tertiaries. But E2 will actually react with secondaries and primaries, and secondaries and primaries are never going to do an E1 type reaction. E1 does actually like the iodines more, so iodines have been more reactive on every single one of our substitution reactions and elimination reactions. All right. And we can actually do elimination with our benzylic and allylic. The nice thing about the benzylic is it can now be a tertiary. Had it been a tertiary benzylic position, you're not going to see E2 do or you're not going to see SN2 do a substitution at all. But it can go in there easily enough and attack that adjacent position and create the double bond. E2 can also happen our allylic position. We're just going to have this come in and attack an adjacent position. It's going out here rather than this one because it will create an pi system. Also, E1 will do the same type of thing, and we almost always get the same products, at least with the benzylic. With an allylic position, though, because that carbocation can rearrange, you get potentially different products. So what I mean by that, had we not had this CH3 there, we would end up with two different double bonds, because this one doesn't necessarily do the same thing. So watch out for your structure in allylic in regard to E1. All right, now here's a factor where it does actually show up. So what I have is we have our double bond, we have the allylic position here, and we rip it off, and we can create the carbocation. But this particular carbocation rearranges. And when our nucleophile rips off the adjacent hydrogen, we end up with a pi system or a pi system. Both times it's the butadiene system, but where it's at in the ring changes. So where it is with respect to that methyl group changes. So our resonance contributors end up giving us more than one product. Now, had we done this one under E1 condition or E2 condition, so strong nucleophile, we would have only ended up with that product. Okay, so that's a factor and it's going to help us out. If you have a primary or secondary alkyl halide, you pretty much have to do E2. If it's a tertiary, it can do both. Tertiaries actually can even do benzylic and allylic with no problem whatsoever. Or S and benzylic and allylic can go through both eliminate E1 or E2 very easily. So the only thing that's really going to make a distinction between these two on which mechanism goes is the strength of the nucleophile. So strong nucleophiles, weak nucleophiles. That's it. Strong nucleophiles are going to favor E2. Weak nucleophiles are going to favor E1. Now, nice little example. We're going to give you these two. I'm just going to ask, is it going to be E1 or E2? And what's our major product? All right, both cases I have secondary, and we know that secondary doesn't like E1, but I also have a strong nucleophile. So both these are definitely E2. And E2 says rip off from the hydrogen that has, or the beta carbon that has more hydrogens. So both these end up giving us the exact same major product. No, that's not true. That one is fluorine. Because it's fluorine, we make the least stable alkyl halide. All right, let's change our nucleophile in that first one. I have just water, but I do have tertiary. Tertiary is, both cases are tertiary, is actually able to do E1 or E2, but this is a weak nucleophile, so this one is going to be E1. Strong nucleophile, this one's going to be E2. And very symmetrical, all the beta positions are the same, so both of these give the exact same product. How about this? Secondary and secondary. Weak nucleophile, strong nucleophile. E1, E2. All right, the E1 creates a carbocation at first. Now, I know we say that it likes tertiary, but remember, allylic is stable enough. All right, so if this actually is our resonance contributor we're focused on, one of our products is going to be I'm going to run out of space here. I'm going to put the double bond down here. We're putting the double bond between these two. But this can resonate. Our second resonance contributor is there, which gives us a second alkene. Which is not the same as the first. So we have two different alkenes that get formed when we go over as E1. But if I'm doing E2, we're only going to attack that because it creates the conjugated system. CH2, conjugated system. Okay, here's something interesting that happens. Turns out when that halogen gets kicked off under E2 positions, or an E2 mechanism, the hydrogen and the halogen that leave need to be anti-perplanar. They need to be on the same plane but on opposite sides. Nucleophile is going to come in here. It's going to force this to come down and make that double bond. All right, reason that's important, these positions are going to be rigid. because that rotation forces it to be one way only. It needs to be that anti-attack. Now, E1 doesn't need to worry about that because first step in E1 is we kick off this and create a carbocation. That back end can rotate all at once. But E2 has to do it from this standpoint. All right, what I mean by that, when we have a particular molecule, they need to be able to rotate where the halogen and a hydrogen can be opposite one another. But once they are, those two groups get rigid in place, which would guarantee we'd have a trans. Now, since this one can rotate, what we're doing is having the back end rotate 60 degrees, we could have the other hydrogen come in there, and we get the cis. Now, because the cis would have to have these two groups closer to each other, it's a little bit less stable, so therefore it happens a little less often. Now, it's not fair to say we always get the E version. What is better to say is the bulky groups, not the high priority group. The bulky groups get as far away from each other as possible. And the other thing that factors in, if these were two different things, like if this is a CH3, we're only going to get that one rotation. It's very going to be rigid. We don't get E and Z if we only have one beta hydrogen. And that was just summarizing why E is major, and it's not E, bulky groups E. Are E in the major product. All right, now something else that factors in. Excuse me. Not that. And something else that factors in. When my beta position has just a single hydrogen, the rotations suddenly become very important. Now, when this molecule was drawn out, the book goes out of their way to put the halogen and the hydrogen on the same plane, and then everything else is wedged out or dashed in. But they went out of the way to do that backbone because that gets it on the anti-planar, so anti-perplanar structure. But when we draw like that, what's going to happen is the two wedged things end up on the same side, and the two dashed end up on the same side. But on this particular molecule, because that beta position only has one hydrogen, you don't really get E and Z. You only get one of them. So when that beta position is actually only has one hydrogen, you only get E or Z. You don't get both. All right. Under E1, a little bit easier to deal with because that first step creates that carbocation, and then our double bond goes here, here, and here. All those beta positions. All of those happen. That one has just one hydrogen, so Zeitze would say that's a little bit more stable, and therefore we would predict that to be our major product. And two groups, E and Z. But we also have the other ones pop up as well. So I'm going to have the double bond go up. Don't expect that one too much because that upper position had all those hydrogens. And we wouldn't expect this one to be that much either because the other one has two hydrogens and we're taking off one. But we would actually end up seeing all of these. And this one does have E and Z. So this particular reaction under E1 conditions, we get 5 products. All right, so a summary of our stereochemistry. SN2 does give us only the inverted product, where the stereocenter is inverted. E2 gives us E and Z. Excuse me. And it gives us both But if our beta position only has one hydrogen, you get E or Z. And you actually would need to look at the stereocenter to figure out which configuration you get. If it's a reaction with SM1, you get R and S, generally a little bit more inverted. And if it's E1, you get E and Z. Excuse me. And you end up with both on E1. Okay, something else that's interesting. When we're dealing with rings, there are certain ones that will not actually do elimination, even if there's hydrogens adjacent position. What I mean by that, if I drew it flat, I have this hydrogen, and this is my halogen. The positions have to be opposite one another, so they could actually form this anti-coplanar. And if I had actually made this and put a CH3 there and put a CH3 up here, this particular one will not do an elimination because there's no way I could replace a hydrogen on that second position. Because even if this other position is a hydrogen, there would never be a way to get them to be anti-coplanar. So the eliminated positions must be in axial positions, and they must be alpha beta to one another. Now that does limit us. So even if this other position is a hydrogen, it is forbidden for it to get ripped off here because there's no way I could have that one on that same plane as the halogen. So it does actually change things. So, excuse me. What we will see is our leaving group, the halogen, must be able to get into that axial position if I've done something that eliminates that possibility. Put bulky groups here. Because that bulky group is always going to want to stay equatorial, that's going to force this chlorine to stay equatorial, even though they're close to one another. That's going to forbid it from actually doing an elimination reaction. Because to do an elimination reaction, I need to get this into the chair conformer where it's axial. But once it's there, we can eliminate it. And don't worry about this. All right, here's where this gets to be interesting. When I have that chlorine leaving, if I can get it in the axial position, I need a hydrogen that's adjacent to it, that's also in an axial position. Because of that, this particular reaction could happen where the double bond goes either way. Now, it will favor this because this had just one hydrogen. This one technically has another hydrogen. So one hydrogen is better, so we end up with this. But we would also get, on that particular reaction, this would still be CH3. That would be a CH3 but double bond could be here because that is allowable. But this would be major because one hydrogen, two hydrogens. And something else that helps us out, since both these two groups are equatorial, that's going to help force this chlorine to be in the axial position always. So we're going to get a lot more rapid reaction with that particular molecule. However, if I actually put all of my groups equatorial, the only way for this to react is to get all of them axial. And in this case, to get all of them axial, this thing's axial as well. It's in my way. I actually can't make an elimination there, so I'm only going to get that one product. Now, it can happen, even though that puts three bulky groups axial, it will happen enough that we actually will see some elimination. Just that one's going to be a harder reaction to go. Probably have to add a little bit of heat along too with everything. All right, E1 in cyclohexene, you don't have to worry about that, but you will form the more stable carbocation most of the time, and then therefore the more stable alkene. Now, last weird thing we have to worry about is our competition of reactions. So E1 and SM1 compete with each other, and E2 and SN2 compete with each other to a degree. Now, what I mean by that, what I have here is I have a strong nucleophile. So this is either going to be SN2 or E2. In this particular case, we have a primary alkyl halide. And we already said that E2 prefers tertiary, but there's no reason not to expect this reaction could occur. So a primary alkyl halide could do a substitution or elimination. What we are going to find is when they compete, though, substitution is always favored, and that's mainly because of that attack. If substitution is possible, it's a little bit easier for it to directly attack that more electrophilic carbon than it is to attack a hydrogen that's off to the side, minding its own business. So the substitution product is always more favored. Then another weird thing happens. We think back to what we know about alkenes. When an alkene like this do a hydration with water floating around in it? Yeah. Those two do react to form, well, they form that. So substitution is going to be our favored outcome when we have something like a primary. All right. Now, we do see that shift some as we get a little bit more steric hindrance on our primary alkyl halide. So primary alkyl halide, both cases, but we got some steric hindrance here. That steric hindrance creates a more stable alkene, so we start to see a shift towards that being a favored product. So it's not necessarily the stericness that's hindering this reaction or causing it to change. That is a factor. We're also getting a more stable alkene. So it's a little bit of balancing act between that stability of the alkene and how easy it is for this bulky thing to come in there and attack and do a SN2 reaction. All right, so we are going to see that our driving factor mostly between distinguishing between SN2 and E2 is the type of alkyl halide. Primary favors SN2, tertiary favors tertiary favors E2. Secondary, you're always going to have a little bit of competition. All right, bulky nucleophile will also change the rule some. Bulkiness is almost like tertiary, and we're going to see a bulky nucleophile favors elimination. It's such a cool feature that we have these two weird nucleophiles that are very basic and very bulky. These will almost never do substitution. These are almost guaranteed to actually create an elimination product. Excuse me, our strength of our nucleophile also factors into it. So having that O negative is what you need to be a strong nucleophile. But a bulky or a weak base of a negatively charged ion, so carbonyl type thing, so the acetate ion, tends to favor substitution. If it's a straight base, a very strong base, it's going to favor elimination most of the time, especially on our more secondary type positions. Right. Temperature also causes a difference. Lower temperatures tend to favor substitution. Higher temperatures tend to favor elimination. Tertiaries, because they are tertiary, are pretty much only ever going to do elimination. Now, SN1 and E1, here's the problem. They're always going to compete. If you have the conditions that favor SN1, that's going to be a tertiary alkyl halide and a weak nucleophile. That also favors E1. So whenever this happens, we get mixtures. So we typically want to choose a situation that we're okay with the mixtures or we're okay with converting one to the other. Tertiary alkyl halides, for example, since they do favor SM1 conditions and E1, it seems like that'd be a good choice. But if I actually were to react tert-butyl bromine with alcohol, I do indeed get a substitution product and elimination product, favoring towards the substitution, but I will get mixtures, definitely get mixtures here. However, if I do them under SN2, E2 conditions, so a strong nucleophile, I pretty much only get the elimination product. Now, there's not much I can do to guarantee I get just the substitution product, but I can kind of, I can probably handle that a little bit more because it'd be easy enough to purify that ether and an alkene. But if you want the alkene, just do it under elimination. All right, so our classes of halides and the type of nucleophile drastically influence us. Now, there's going to be times we can't avoid mixtures. So you do need to actually make sure you see how to do this, because while we will have opportunities to avoid mixtures, certain times you can't. You're always going to end up with that as a possibility. All right. Last little one that we're going to look at here is an actual example of a substitution reaction to make something. It's actually called Williamson ether synthesis, and it is where we're going to make an ether using an alkyl halide and our alkoxy, or even an alcohol. But we're actually choosing this to an alkoxy because that forces this to be an SN2 type reaction, and we know that favors a substitution. So RO just comes in there, does a backside attack, and we get an ROR. And making the alkoxies are relatively easy. You just take an alcohol, you treat it with sodium or sodium hydride, and that just actually rips that off, and you get this. Matter of fact, these two together, you can actually, if you let that water evaporate off or heat it off, you can make a salt of that. So a sodium methoxide or sodium ethoxide, and you can actually have that as a solid to use as a base. So once you have that, you just add that to your alkyl halide and you've made your ether. Now, theoretically, you can do this with just about any alcohol and any alkyl halide and make any ether. And like if you want to make butyl propyl ether, you could start with propyl bromide and butoxy ion, or you could do butyl bromide and propyl oxide. And both of them would give you butyl propyl ether. However, we do want to be careful of our choices, because if I wanted to make tert-butyl ethyl ether, I could use tert-butoxide and allow it to do a backside attack on ethyl bromide, and we'd get our product. But if I try to reverse these two, now this is a tertiary alkyl halide, this is not going to do a backside attack, it's going to do an elimination. So generally speaking, we want this less substituted, primary or so. This one we don't really care about so much. Reverse that. We want this one primary so, because we're going to do a backside attack. To favor SN2, we want this primary. This doesn't necessarily matter, but it does factor into it. We do need to be able to get it in there, because this being bulky doesn't guarantee the ether. We do get mixtures here. All right. Excuse me. What we're showing here is using our elimination to create our alcohols. And what we're focusing on is, while we might want to make a alcohol, choosing our starting ingredients to favor the substitution can benefit us. So what I mean by that, we know this is going to be SN2 because we're using strong nucleophiles. We have a secondary or a primary. Secondary doesn't strongly favor substitution. It actually starts to favor a little bit more of elimination. Now we can control it some with temperature, but a lower temperature, while it does give us more substitution, we're always going to have some elimination products. However, if we had actually chose a primary alkyl halide, our strong nucleophile is going to strongly favor substitution. All right, so we want to plan this out. So when you decide what you want to make and what you're starting with, or vice versa, you can actually predict your conditions that would give you the product that you want. So right now I have a tertiary alkyl halide. I know if I use a strong nucleophile, I'm favoring substitution and elimination. And more importantly, I'm favoring elimination. because strong nucleophile, tertiary, we're getting nothing but elimination. However, if I put an H on here, suddenly this is store stable for substitution and elimination. And whenever they compete, we know that substitution is typically major product. So our conditions can drastically change what our major product is, and even if we have mixtures. Now, alkynes that we introduced before, we can do a substitution or we can do a synthesis. It is an elimination, but we're going to see we have to do it kind of twice. All right, so we are doing an elimination where we're going to just rip off an adjacent hydrogen, and we create that. And while we said that vinyls don't like to do substitution, they can still do elimination. And what we find is, when you have a competing little hydrogen, so what I mean by that, let's put CH2, Br, and another CH2, and we'll do an R prime. Both these are beta positions, and one of those is going to get chosen for our double bond. The second bond always go to that same location. So you end up with an alkyne always. And if you use a vincinyl dihalide, so where the halogens are on adjacent carbons, you also end up with a triple bond. But it gives us a way of actually making an alkyne using an elimination type of reaction. It just doesn't necessarily just need to end with an alkene. All right, alkenes to alkynes, actually kind of easy to do now. So what we would do is take our alkene and react it with something like a halogen, bromine, and actually make the dibromide. And then just do 2 equivalents of that NH2 that we just introduced, and we would turn that butene into a butane. All right, that finishes up with our chapter, and do make sure you go through some of the problems in there and fire away with any questions you possibly have.